Yeah, very good afternoon to everybody. So it's a pleasure and honor to have Sayan Choudhury, who is a product of IISER Kolkata first batch. He joined IISER Kolkata when we were in Salt Lake in the year 2006, and he graduated in the year 2011. He did his master's thesis with Professor Panigai and Siddharth Lal. And Sayan did his PhD in Cornell University on quantum condensed matter. Subsequently, he did a postdoc in Purdue University and then in Pittsburgh. And he has now recently joined the faculty of HRI, Harishchandra Research Institute in Allahabad. And it's really an honor to have these people come back and join us faculty in India. So today, Sayan is going to talk about on non-equilibrium dynamics of quantum matter. Over to Sayan.
Okay, thank you. Let me just check if this thing. This also needs to be put up.
This way. So see, no, it has to be. It's on. So it goes like this. Sorry, it's off. No, it's on. So it goes like this. Wait, it'll take some time. Why is it? The pointer is there.
Pointer is there. I will probably I can use this computer.
Yeah. Okay. Maybe it will take some time.
Okay, no problem. No problem. Okay. So, it's a real pleasure to come back to IISER. It's my alma mater, and I'm very excited to talk about non-equilibrium dynamics of quantum matter. The idea of this talk is I want to keep it very pedagogical. So just ask whatever questions come to your mind at whatever time. There is no particular point that I want to reach within a particular time period, and there's plenty of time. Okay. So with this, let me start off. Even this is not working, looks like. QIQT. This is now working also. Okay, so this is all it's got. Okay. So in particular, I'm going to talk about non-equilibrium dynamics of a very particular type of quantum matter, which I call synthetic quantum matter. So the outline is the following. I want to give you an introduction to synthetic quantum matter. And then there are two particular points that we can get to at the end of this, by the end of this talk. There is a part on time crystals, and then there's a part on information scrambling. The goal is that the time crystals part should be covered. If we don't get to information scrambling, doesn't matter. If any of you are interested, we can talk after the talk. Okay. So with this, let me start off by giving you an introduction to synthetic quantum matter. So what is this? So before I talk about synthetic quantum matter, I want to first talk a little bit about quantum matter. And quantum matter is inherently very fascinating. It's the kind of collective behavior that we see when quantum mechanics comes together and plays with several degrees of freedom. So when you have several degrees of freedom, then you can see a lot of exciting collective behavior. This can include superconductivity, it can include topological phenomena, fractional topological phenomena. You can get systems which show fractional charges, or you can get systems where you have fractonic systems where the individual degrees of freedom cannot move, but a collection of quantum particles can move together, and so on. So these are inherently very exciting systems, and this has been the subject of study of quantum condensed matter for several decades now. One really fascinating thing that emerged with the beginning of the 21st century was the realization of the so-called synthetic quantum matter. So synthetic quantum matter is essentially a collection of cold atoms or trapped ions, where these atoms are put together in inherently very, very controlled geometries, and you can control the interaction strengths in the system, you can control the interaction range, you can control the geometry. And this whole thing really started with the realization of superfluid to Mott insulated transition that was seen with a system of bosons trapped in an optical lattice. But now this field has really progressed forward very fast, and the systems can be thought of as a variant of Legos. So just like we can put together Lego pieces to build a variety of different things, you can do whatever your imagination takes you to. With these kind of designer platforms with cold atoms or molecules or trapped ions, you can actually build a lot of different things. So in order to give you a sense of the kind of control these people have, here is a collection of Rydberg atoms which have been combined together in the form of the Eiffel Tower. So this is the sort of control of the geometry that one can get. And so this is an amazing playground for theorists, because you can essentially think about building a variety of different models, and you can make very accurate predictions for experiments. You can tell what kind of experiments can be done, what will be the predictions. And the real experimental systems, of course, are incredibly complex. This is what it looks like. You have a collection of vacuum chambers and magneto-optic traps and cold atoms. And whenever I go into one of these labs, it fascinates me that they're actually able to pull off this kind of miracle and bring up, realize this very exciting kind of physics. Okay, so there are quite a few platforms that have now been developed where one can realize these different kinds of synthetic quantum matter. These include cold atoms in optical lattices, trapped ions, photonic quantum processors, Rydberg atom arrays, or cavity quantum electrodynamic systems where you have atoms put in a cavity where the photons mediate interactions, and superconducting qubits. And all of these systems are forming the backbone of what is now called the second quantum revolution. Wanted to put this in because this is a conference on quantum information and quantum technologies. And so these kind of systems, on the one hand, are very crucial for exploring many body physics in this synthetic quantum systems, but they can also be useful for quantum information processing. So if you look at what are the kind of future goals with these systems in terms of quantum technologies and in terms of quantum many-body physics, one of the goals that sort of motivated a lot of this work in the first place is the quantum simulation of models that are beyond the reach of state-of-the-art numerical methods. So this was a vision that was first propagated by Feynman when he proposed that inherently simulating quantum systems is very difficult because your Hilbert space grows exponentially with the system size. So if you want to simulate, let's say, 10 spins, you need to have 1024, an array of 1024 numbers. But if you want to have simulate 100 particles, your array needs to have a dimension of 2 to the power 100. So, and very soon, even if you're using all the atoms of the universe as a quantum bit, you would not be even able to simulate a quantum system of the size of a grain of sand. So the idea that Feynman had propagated was that if you have a real quantum system that can simulate the actual sort of many-body model, then you can have a quantum system simulating another quantum system. And that was one of the main motivations for a long time, was to actually realize, for instance, the Hubbard model and try to see what's the phase diagram of the Hubbard model by a quantum simulation. The next kind of goal here is to realize synthetic quantum matter, which can have novel properties, which may be very difficult to realize in other condensed matter systems. A sort of example of this is something like a supersolid, which has been realized with dipolar quantum gases. Now, supersolids, our first, have been talked about for a long time, and there was a time when there's a lot of excitement that supersolids have been seen in superfluid helium using helium. And that turned out not to be the case, but nonetheless, using cold atoms, you can realize supersolids, for instance. So there can be this kind of synthetic quantum matter with emergent properties, which may be very difficult to see otherwise. The third is to explore non-equilibrium dynamics with synthetic quantum matter. Now, this is very exciting to me. This is, in fact, what I'm going to talk about a little bit today. The idea with this is that you start off your system in some very highly non-equilibrium state, and you want to see how the system evolves. What are the universal features that are associated with non-equilibrium dynamics? And this turns out to be something which can be done reasonably well using these synthetic platforms. You can have control over the model that you create. You can have control over the initial state that can be realized, and then you can explore the dynamics that comes about. And of course, the final goal here is to build a real quantum computer. Today's talk is going to be on this topic of exploring non-equilibrium dynamics, right? So with this, I'll get on to the first topic, which is that of Floquet time crystals. So Floquet time crystals goes back to this very old question of how does one classify phases of matter, right? And the first sort of insight into classification of phases of matter comes from Landau and Ginzburg's idea of spontaneous symmetry breaking, that you classify a phase of matter by the symmetry that it breaks, right? So if you have a solid, it breaks the translation symmetry and so on. And these ideas were, of course, put forward, taken forward by Wilson and Fisher, who came up with the renormalization group ideas to actually classify these phases of matter. So this is, the so-called Landau-Ginzburg paradigm, or Landau-Ginzburg-Wilson paradigm, or Landau-Ginzburg-Wilson-Fisher paradigm, and so on. And now this breaking of these symmetries, the spontaneous breaking of symmetries that leads to realization of phases of matter, has some important consequences. So for instance, crystals is a great example where spontaneous symmetry is broken. So we spend all of our condensed matter 1 course studying crystals, and the crystals emerge because you have a Hamiltonian which is translation invariant, but this translation symmetry is spontaneously broken in a crystal. So this is one of the very paradigmatic examples of the spontaneous symmetry breaking paradigm. Okay. Now, one question so this is, of course, something that happens in space. Now, in 2012, Frank Wilczek started exploring this question of, can you break the spontaneous symmetry? Can you see spontaneous symmetry breaking in time, right? So normally you have a Hamiltonian, even if you have this Hamiltonian, which is time invariant, can you have a system which in equilibrium breaks this time symmetry, continuous time symmetry? And so for instance, if you have a system whose, let's say, whose equilibrium state or ground state is something which is perpetually moving, okay, so that would be something where the continuous time symmetry is broken. So Frank Wilczek introduced this idea, and he called this system, in analogy with space crystals, as time crystals. Okay, so he put forward something for classical systems, and he put forward something for quantum systems. I am not going to go into the classical example, even though it's actually a very wonderful example of classical mechanics of where the Lagrangian formulation becomes very crucial. Nonetheless, let me get into the quantum formulation and tell you what Wilczek had in mind when he proposed. So what Wilczek had come up with is the following. The essential idea was this: you have attractively interacting bosons in an Aharonov-Bohm ring of unit length. Okay. Now, let's say that you have your interactions are strong enough, then these bosons will clump together and thereby resulting in what is known as a bright soliton. Okay. Now, the central idea that Wilczek had was the following, that you have a bright soliton being formed through this Aharonov-Bohm ring, and then you make a finite flux go through here. And once you do that, what will happen is that this this soliton, this bright soliton here, is going to feel a torque and will start moving around. And so what he proposed essentially was that the ground state of the system would be one where the torque where this soliton is moving around, and so the time translation symmetry is broken, right? And of course, this looks sort of dangerous because it looks close to a perpetual motion machine. You have something where the system is continuously moving in the ground state or in equilibrium. Okay, and it turned out that actually Wilczek's idea was wrong. This kind of system that one gets where the bright soliton is actually moving is not a ground state of the system. It's actually an excited state, and it's not an equilibrium state. So in fact, what was shown by Watanabe and Yoshikawa was that if you have sort of reasonably short-range interacting systems, then you cannot actually break time translation symmetry in equilibrium, okay, and in the ground state or in equilibrium. So that so with this kind of series of works, Wilczek first proposed this in 2012, and then with these later works and in 2015 by this work with Watanabe and Yoshikawa, this seemed to be the last nail in the coffin for time crystals. But the idea was still very exciting, that can you actually realize system which would be able to sustain infinitely long oscillations, okay? And of course, yes. This is a bright soliton, just attractive interactions. So I have a set of bosons. I have a set of bosons. These bosons are attractively interacting, and that will cause. So it's like just a sort of a wave packetish thing, right? Yes. And the fact that it's a soliton is a GP in play. Yes. So, okay. So what we know is, what has been established is this time translation symmetry breaking is not possible in equilibrium. Okay. Our equilibrium system, even if it shows transient oscillations at starting from some state, those oscillations will eventually die out. Okay. But then the question is that if we can't get it in equilibrium, we can still go into a non-equilibrium setting and ask the same question: can we have time translation symmetry breaking in a non-equilibrium setting? Okay, and that has turned out to be a remarkably fertile direction of work, where time crystals have been shown to arise in a variety of non-equilibrium settings. Perhaps the most exciting setting where it comes about, and the most well-studied setting now, is in periodically driven quantum systems. Of course, in a periodically driven quantum system, you don't really have a continuous time translation symmetry because you're periodically driving the system. Nonetheless, you do have a discrete time translation symmetry, that if you change the Hamiltonian by a period big T, let's say, then the Hamiltonian returns to the original Hamiltonian. So here you can actually get discrete time translation symmetry breaking, and I'm going to now discuss how. Okay, and I'm sorry, this was supposed to be a GIF if it was played in Keynote, but now this is just a photo, which will not be very helpful. Okay, but the idea of nonetheless, the idea of this discrete time crystal is that you have periodically driving the system, but physical observables in the system oscillate with a subharmonic frequency. The simplest example is if you periodically drive the system with period T, observables in the system oscillate with a period 2T, or in general oscillate with a period NT. So you have broken the discrete time translation symmetry in the system. Okay, so here what, for instance, we were supposed to show in this GIF, if it had played, was that you're starting off in one minima, and then after a time T, you would go, your particle would be at the other minima, and after a time 2T, your particle would be back to the same minima. But if you looked at just the Hamiltonian, you'd always get these two minima at time 0T, 2T, 3T, and so on. Okay. So how does one realize a time crystal? So let me give you a very simple example where you can get period doubling oscillations. Okay, imagine you have a set of spins. Okay, all of these spins are pointing up, and you imagine that you give these systems a perfect pi pulse. So basically, all spins which are pointing up will now point down. Okay. And then if you give another perfect pi pulse, then the spins will also go up again. seems rather trivial. You give perfect pi pulses, all spins pointing up, we go to all spins pointing down, we go to all spins pointing up again. So if I were to look at some observable, let's say if you were to look at total magnetization, it is positive, negative, positive, negative, and so on. Okay. But the thing is that this hinges very importantly on the fact that you are dependent on a perfect pi pulse. Okay. So this perfect period doubling oscillations happens when you have a perfect pi pulse. So this is a very extremely fine-tuned situation. So what happens when you make the pi pulse imperfect? Okay. So what happens when you make the pi pulse imperfect is the following. The spins essentially are not going to point, all of the spins are not going to point down, they're going to point in some other direction. And now if you keep giving these imperfect pi pulses, the spins are going to point in some other direction again, and so on. So what is going to happen is that once you start giving imperfect pulses, the spins are going to start showing beats. Okay, it's going to show beating patterns where you are, instead of, if you looked at the Fourier spectrum, instead of having a frequency, instead of having one peak at pi over t, what you're going to have is you're going to have a splitting of the peaks, and this splitting is going to depend on what is the imperfection in your pi pulse. Okay, so this is not good, because what it is telling you is that if you were trying to make a time crystal by using these pi pulses and these non-interacting spins, then you get this kind of period doubling oscillation at only at one point. So if you want to make this sufficiently generic, if you want to promote this to the level of a phase that it can happen over a certain region of phase space, so then a certain region of parameter space, then you need to do something else.
There's a series of
Yeah. So basically, you can think about this as the QIQT system. That so if you had a series of pi pulses, then of course you could get this. But once it's imperfect, you get a splitting of the peak, and then this is crucially the splitting depends on what is the imperfection. Yes, Rang.
So like if you apply an imperfect pi pulse, which is, let's say, a theta pulse, if you keep applying theta pulses, it will do a notation in
Yes.
this plane
Yes.
smoothly, no problem.
Yes.
But you need probably another interaction Hamiltonian in every period to get something interesting out of it.
Precisely. You have hit the nail on its head. So what you want to do is to get something interesting is you want to add interactions. Okay. But here is the sort of catch here, that when you are driving an interacting system, generically the system heats up, because when you are putting in you're putting in energy into the system via the drive, and normally if it's a non-interacting system, the system cannot really absorb that energy. But once it has interactions, it can absorb energy from the drive and spread it through the system. And so generically what's going to happen is that the end result of this is that you're going to heat up to a featureless infinite temperature state. Now there have been some proposals on how to evade this heating to an infinite temperature state via some very exotic mechanism known as many body localization. But nonetheless, even if we don't want to, even if we allow the system to heat up to a final infinite temperature state, a question that remains is that, can you get something interesting in the middle? Can you, let's say, get a pre-thermal behavior up to a certain time scale in which you can see this kind of periodic oscillations, and can you control this time scale? Can you let's say make it arbitrarily large? So those would be interesting things to take care of. So the thing, as you said, is that we want to add interaction amongst the spins, and we want to find a way such that the system can evade heating, so at least up to whatever, some kind of exponentially long time scale. Okay. So I'm going to talk about a particular way to evade heating in these systems. There are a variety of other approaches that have been discussed, including, most importantly, many body localization. But I'm going to talk about an approach which I think is relatively sort of easier. So this approach depends on having a system with all-to-all interactions. So you have a system where all spins are talking to each other with equal strengths. Okay. And for the purposes of this talk, I'm going to have all these spins talking with equal strengths, but one can make these vary a little and you can study the effect of this. And the end result is that this is a very special model because you have all the spins interacting exactly with each other with equal strength. But if you make this a long range interaction with, let's say, j over r to the power alpha, then you would still get up to some alpha, you would be able to get pre-thermal time crystal behavior. Yes. No, so we don't actually set that. So because this is so what is going to happen is if I looked at the propagator, so you have a kick term here, which is basically a pi pulse, and then the propagator will have a term of j times t. And what I'm going to argue here is that when jt is exactly equal to pi, then you actually would get eternal oscillations. If you moved jt now slightly away from pi, you actually get oscillations up to a certain time scale. That time scale is controlled by how what is the distance from pi. Okay. Yes. 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 So this when I'm talking about this j, I have put in the 1 by n. Yes, but generally, yes, there you want to have a 1 by n dependency. Yes. So you have this uniform all-to-all Ising kind of interaction, and you give this system a periodic kick. Okay. And then what we show is that essentially the system exhibits eternal period doubling oscillations for any value of this epsilon, as long as your jt equals pi and the number of particles is even. This is a special point which we can show analytically. Away from this special point, we can do numerics. Okay. One thing that the reason, sort of before I go in, the reason why this works is that this model can be mapped to a model of a kick top. So this kick top has regions where you can get regular motion and regions where you can get chaotic motion. So essentially what you are doing is that you are moving in the period place where you have regular motion, and you are using this to go between 2 points where you get period regular motion. And now if you moved away to a place where you had sort of irregular kind of chaotic motion, then of course everything is lost. Okay. So let me tell you what it does. The essential point is the following, that the reason why you get perfect periodic motions here for jt equals pi is that if you started off with some initial state, I'm going to tell you about one particular initial state. If you started off with a state where all spins were pointing up, okay, and then you gave this imperfect pi pulse, what would happen is that you create a bunch of states in the middle where all of these states come out some amplitude. Okay. Now, these amplitudes were such that there is a sign here, and then there is these amplitudes. These signs are like this, that these have alternating signs of plus, minus, and so on, where you basically have a sign of -1 to the power m. Okay. And then, so this is just the geometric phase that is coming because of this flipping. And when you create this jt to be exactly pi, what happens is that you have a dynamical phase that it acquires of essentially exactly again equal to -1 to the power m. So what is happening here is that this dynamical phase and the geometric phase cancel each other out for this particular point, leading to an exact recovery of the initial state. And so this return, and this you can actually show for any, starting off with any product state, you can sort of make this argument. And then the return probability after 2 pulses is 1, so which essentially means that the return probability after 4 pulses is 1, 6 pulses is 1, 8 pulses is 1, and so on. So which basically means that you will have a perfect constructive interference here, and this will lead to a sort of recovery of the initial state after for any initial state for every even values of pulse. Okay, so if we look at JT equals pi, you get exact return probability at 10. Oh, sure. Okay, so the question is that it means time crystal is connected with spin, not time. Is there any connect? No. Of course, time crystal is connected with time. We are doing a particular spin model to show that your system state is recovered after a time 2t, 4t, 6t, 8t, and so on. So the discrete time translation symmetry is broken here. This is being done on a particular model, which is a spin model. Nonetheless, this is of course time translation symmetry breaking. I mean, you can do it on any kind of model. It can happen with fermions, bosons, even classical systems. So yeah, time crystals has nothing to do with spins. It's just to do with time. Okay, so if you do the okay, and we seem to have lost this thing again. Okay. Yes.
Alt tab. Alt tab.
Yes. Perfect. That works. Okay. So, and if you look at other kinds of observables like local magnetization, for instance, you would find that this is recovered. Okay. And so this is something that you can see for any kind of initial state. This is something that we checked out. I'm not getting into the details of this, but the essential idea is that you have an approach where through all-to-all interactions, you are using cancellation of the geometric phase and the dynamical phase to realize this a recovery of the initial state after every even pulse. Okay, so this is a sort of so this is reminiscent of a spin echo, but where interactions play a role. Yes.
How robust is this scheme as you change epsilon? Because that is one of the major point. I mean, like, yeah.
Perfect. So actually, you will see this perfect recovery here for any epsilon. So that is the major thing, that after what this does is that after 2, 4, 6, 8 pulses, you always return to the initial state. Of course, if epsilon was exactly equal to pi, for instance, then of course it would be up, all up, going to all up, going to all up for every t, 2t, 3t, and so on. For any value of epsilon other than pi, you would go to some other state in the middle and then recover. So it is true for any epsilon. So here, but one can say that while this is true for any epsilon, this is for that specific value of jt being equal to pi. But what I am not going into here is that if we remove it a little from pi, you will still be able to see these oscillations go on till a particular time, and it will not be exact recovery, but this is an exactly solvable point where you will see this recovery happening for any epsilon. So this is kind of reminiscent of a spin echo in many ways, where you get back your initial state, but nonetheless where the thing is done via interactions. So okay, so this eternal period doubling oscillations, you can observe this for any initial state. And the other thing that I also want to say, that while I have been discussing here the case of having all the spins getting the same imperfect pi pulse, you can ask this question of what happens when these epsilon varied spatially. Now, this scheme is so robust that you will get it even for, yeah. So that is very nice. So this is great. So this is yes. So spin echo. So this there is this question of robustness that comes about here also, that okay, so we are doing this at jt equals pi, right? So what happens when you are not, when you move away from these particular exactly solvable point? The reason why we are calling this a time crystal is because even if we move away from this exactly solvable point, you will actually see these oscillations still continuing, and that has to do with the fact that this is actually a kick top. So yes. Yeah. Yes, sort of, yes. So this actually is essentially a mean field model, really, because you have these all the spins interacting with each other, but you can sort of move away from it a little bit by, let's say that now instead of having all spins interact with the same strength, you make it a long range interacting model. You call this a J over R to the power alpha. So, and and the J is appropriately normalized. There's some CAC normalization which does the job for you. So in that case, what you would find is that as long as your alpha is less than 1, essentially, this kind of mean field behavior actually stays. So, so you are going to get these kind of oscillations. Now, of course, for those kind of models, we cannot, this model one can actually sort of do a semi-classical analysis. For those models, you have to be doing a finite sized system. So I'm telling you my conclusion based on finite size studies, but looks like it works. Yes. Yeah. But the mean fieldness is important because in some sense it gives you a way to stabilize the system without heat. So interactions are needed to stabilize the time crystals, but it also prevents heating because in some sense in these kind of mean field models, what happens is that the number of states that it can go to is far more restricted compared to a generic non-integrable model. So that is sort of one of the reasons why you can get this kind of, yes. Yes, yes. Randomly, the imperfect path is yes, yes, yes. Then how guarantee it is another imperfect path? So that is the yes. So that is the thing that for this particular, let's say that for this particular value of the interaction strength, we can make this 100% sure that you will get back. So this was sort of whatever the imperfection had done, this interactions will recover it. Yeah, so that is guaranteed for this model. But what we are demanding was that these pulses be perfectly periodic. So at every point you give the same sort of imperfect pulse. And so one question that I'm going to discuss a little bit now is that what happens when this drive itself is no longer periodic. So if your drive lacks periodicity, can you still recover a time crystal? Can you still get periodic oscillations? Okay. So the answer to that is yes. And I'm going to give you sort of a model where a variant on this model essentially, where you can get periodic oscillations in a system where the pulse strengths at every period t is going to be a little different. Okay, so the model is the same, and now I have normalized this properly, which I forgot to do last time. But yeah, so you have this uniform all-to-all interactions, and you give it a kick which is aperiodic. And by aperiodic kick, I'm doing a very specific form of an aperiodic kick. I was telling that you have these epsilons here, which you're globally kicking, but let's say that these epsilons were chosen randomly. What happens to the system then? Okay. Now, so T is fixed here. So we can play around with that as well. So what? So that can also be done, and that was what we wanted to do in the first place, and then turned out that in that case you get nothing interesting. The system just thermalizes, or maybe something will come about if we do play around with it. So but that is a sort of, I don't know, felt like a stronger form of a periodicity. So what we tried initially was that this time point when this was being applied, we would make it go between say some t minus delta to t plus delta, where this minus or plus was chosen randomly. So that was the initial point, and then we found that systems thing was just thermalizing. We couldn't really get too much there, but here if we were instead playing around with the strength of the kick, that whatever is the strength, that we will change. Now there we actually get something which is interesting. Of course, if we were to actually do a totally random drive, even there you don't actually get anything interesting. The system just thermalizes. However, if you have some kind of structure in the drive, and there is something in the chat, I should probably take a look. Question: which type of system we are interested to simulate with time crystal? No. So we are not trying to simulate a particular system with a time crystal. A time crystal itself is a phase of matter. It's a dynamical phase of matter, and which breaks time translation symmetry. Now, it turns out that these kind of synthetic quantum systems are particularly suitable to realize these kind of state of matter like a time crystal. So that's why talking about, yes.
That in future they should unmute and ask the question rather than type in the chat.
Yes, that's a very good point. So in the future, please unmute and ask the questions instead of typing it in the chat. Okay. So with this, let me return to my talk.
Alt tab.
Alt tab, alt tab, alt tab. Okay. Where did it go? Yes, I think that should. Yes, that takes care of things. Okay. So that is the particular thing that we're going to look at, where we change this here. Okay. And it turns out that, of course, for a random drive, the system just thermalizes. However, if your drive has some sort of structure, then the system can actually evade thermalization up to very, very long times. Okay. I'm going to talk about a very specific structure to this aperiodicity called a quasi-periodic drive. But in the end, I'm going to make a comment about more general structured drives. Something which goes between a quasi-periodic drive and a random drive. Okay. So let me first tell you what the results are, and then tell you sort of what we did for this. And if you, again, as I mentioned, if you have further questions, we can discuss. But the result is basically the following. If I were to take a Fourier transform of the drive amplitude, it has all these various different forms of peaks. If we are taking it from a quasi-periodic drive, I'll tell you the specific form of the quasi-periodic drive. But if we looked at the response shows a sharp peak. And this kind of a sharp peak in Fourier space is the signature of a time crystal. Okay. So what we do is that what we show is that this spin chain, it will still show periodic oscillations with a rigid period if the kick amplitudes are drawn from a particular periodic drive known as the Thue-Morse sequence. Okay. So what is this Thue-Morse sequence and why does this work? So let me define the Thue-Morse sequence for you. So the Thue-Morse sequence is the way that we're going to do it is the following. The first term of this Thue-Morse sequence is 0. You take tau 2n equals tau n, and tau 2n plus 1 equals 1 minus tau n. Okay. So if you looked at the first few terms of this series, the first term is 0, the next term is 1, then the next two terms are these 0 and 1 alternated. So the next two terms is 1 and 0. So if you look at the terms that come after this, the next 4 terms are an alternate of these 4. So it becomes 1 0 0 1. If I was to do the next 8 terms of this series, you would get the alternate of this. Okay. So what you see is that every 0 is followed by a 1, and the system has a very specific structure where you can imagine that you started off with a dipole, then after 4 it became a quadrupole, after 4 it became an octupole, and so on. So at a very basic level, this sequence is composed of effective dipoles. And if I were to look at this kick operator in a model, right, and if I were to look at the time evolution operator, you would find that after 2 pulses, your time evolution has a form of either U1 U0 or U0 U1, because you're always composed of dipoles. Okay. So then the point is that in the high frequency limit, what you can do is this U1 U0 and U0 U1, these effectively in this high frequency limit, these become almost equal, and you can get an effective propagator, effective time evolution operator, which is a Floquet, which has a Floquet form. And this arises because you always have this kind of dipolar operators here. Okay. Now this of course means that you didn't need to go through a quasi this Thue-Morse sequence. You could have random dipoles, and that should be enough to actually give you a pre-thermal time crystal. And that actually turns out to be true if you take random dipole, a sequence composed of random dipoles, then you would indeed get a perfect, I mean, you would indeed get a time crystalline behavior. But the time up to which you would get this behavior is controlled by the kind of randomness that you have. So with this random dipolar drive, you would get it up to a certain time. If you have more structure and you did a random quadrupolar drive, you would get it to a longer time, and so on. And then your final end point of the sequence is the Thue-Morse sequence. So due to this effective Floquet propagator, you will end up getting this kind of time crystal order. One point that I want to mention is that this is not really a time crystal, because what you are doing is that your system actually does not have discrete time translation symmetry. It has some kind of time translation symmetry on average, because if I look at 2 or 4 or 8, 6 or 8 of these, then this has some sort of effective time, average time translation symmetry, but it really does not have the actual kind of translation symmetry. So even though I'm using the term time crystal here, it's sort of not a very good use. Yes.
Like I think some experiments were done not very recently, I think 2 years back or something around this time.
Right.
So when they had the coupling, and they also applied a drive.
Right.
Okay. And then the pi pulse is separate. They applied a short pi pulse.
Right.
So they I think observed some kind of Floquet heating during the first part.
Correct.
So, but in this case, you won't get Floquet heating because it's your drive is really very short, right?
Right. I mean, you will eventually heat up in these systems. What the Floquet heating will eventually come. So the point is that there are two parts to it. One is that these kind of phases here appear actually as a pre-thermal phase. So you start off with a state which you can first go through some sort of Floquet heating to reach a pre-thermal plateau, which is at some effective temperature of an effective Floquet Hamiltonian, which you can sort of do some sort of a Magnus expansion and get an effective Floquet Hamiltonian. But this Magnus expansion thing is going to break down after a certain time scale, and the system is eventually going to heat up to an infinite temperature state. So there is no, unless you have some kind of let's say that with something like many body localization, the idea was that you have emergent integrals of motion, and unless you have that kind of an emergent integral of motion, you kind of have some variant of integrability in this system, then you have very few conservation laws, so system will just heat up. But what happens with these kind of systems is that we have a time scale, and by controlling the frequency, let's say, you can actually control how long will this time scale be. One of the sort of ideas with these pre-thermal phases is that high frequency driving will lead to a longer time scale for pre-thermalization, because what happens is if you have a high frequency drive, then very roughly, instead of one spin flipping, a large number of spins have to flip together in order to absorb a quanta of energy from the drive. So that can sort of control the time scale. Okay. So these time crystals are actually pre-thermal. If I did it for starting with that kind of very symmetric initial state, if I look at various system sizes, you would find that this Floquet heating that is appearing eventually, any kind of time crystalline order parameter will eventually die. That is independent of system size beyond a point. So while for real dynamical phases, it would actually increase with the system size. And then these are robust against various perturbations. So we have checked against a variety of different kind of perturbations and checked that indeed you can get this time crystal order. Okay. And there are a variety of different realizations of this kind of long range interacting models. You can get this with spins coupled to cavities, you can get in ion traps, or you can even get it using bosons in a double well, or variants of kick top models, for instance, will lead to this kind of all-to-all interacting behavior and time crystalline behavior. So all-to-all interactions can appear. So with this kind of spins coupled to cavities, for instance, you basically have photons, and or ion traps, you have long-range interactions. So yeah, so one thing is that for this exact all-to-all, the good part about it is that we can do simulations for longer system sizes. But what we have also checked is that, let's say you have a 1 over r to the power alpha. We have checked whether if you have this alpha large enough, can you still get this kind of time crystal behavior? And we do indeed find that you can get it. And you can also do, I did not go through this, you can do an effective sort of spin wave kind of theory around the mean field grounds, the mean field state, let's say, to justify that indeed, at least pre-thermally, you expect the time crystals to be stable. So what we have done is that in this, we have proposed a way to realize time crystals by optimizing the interaction strength, basically by optimizing JT. And this time crystal can exhibit a perfect revival of the initial state after an even number of pulses. And we have demonstrated that such kind of behavior can persist even when the drive becomes aperiodic, albeit with a certain form of structure in there. And this can potentially be realized in a variety of different quantum simulator platforms. Okay, so how are we doing on time? Now, officially, I'm over time, but okay. So what I'll do is, there is a second part to this talk. I will start it, give you a brief introduction. What was supposed to be this? My goal actually was to reach to the first part. That's it. So anything that we do now is like a bonus. Yeah. Yes. Okay. Okay. So the second part of this talk relates generally to this notion of non-equilibrium. So the first part we were doing a particular form of non-equilibrium dynamics, which is driven systems. Okay, so you're talking about periodic driving, a little bit about aperiodic driving, but these are driven systems. The other driven isolated systems, but nonetheless driven systems. The other kind of non-equilibrium protocol that one can think about in this kind of isolated systems is to think about quantum quenches. So the idea is that you prepare your system in the ground state of some Hamiltonian, and then you suddenly change the parameters of the Hamiltonian, or you prepare your initial state in some way which is very different from the eigenstates of the Hamiltonian, and then you let your system evolve, right? So what are the sort of, what's the final state that you would reach here? What are the different things that can happen here? So if you look at isolated quantum systems, generically, there are two kinds of behavior that one sees. One is that the system can thermalize, which essentially means that any kind of memory of this initial state is lost, or the system can localize, which means that the system can retain the memory of its initial state. So a time crystals, for instance, is an example in some sense of localization, because you are recovering your initial state, so you have memory of the initial state. So this is a cartoon picture of an experiment that was done in Munich, where atoms were loaded in the odd sites of an optical lattice, and the system was allowed to evolve. And then if we looked at this density profile, then when the system thermalized, the density became uniform, and the system localized, then you still have some kind of structure here in the density. You can still get a density wave. Okay. So localization is typically observed in strongly disordered systems. There has been some interesting debates about it in the recent past, which I am not getting to. And thermalization is typically observed in non-integrable systems. The idea with non-integrable systems is that you have very few integrals of motion. So if you start off with a quench and you want to look at what's the long time behavior, so this is standard statistical mechanics, you know that your long time behavior is going to be determined by the few integrals of motion that you have. If you have very few integrals of motion, you will just go into a thermal ensemble. If you have an extensive number of integrals of motion, you can get localization. You get what is generally known as a generalized Gibbs ensemble, which takes care of all the integrals of motion. Okay. Now, for the isolated quantum systems, one question that is interesting is that if you look at the total system, it's evolving unitarily, and what do you mean for such a system to thermalize? Of course, we don't know this answer from StatMech. The answer is that basically the system can act as its own bath, bringing subsystems to local equilibrium. So if I looked at the reduced density matrix of a subsystem A, then it is basically being described by some thermal ensemble. So you cannot distinguish this from being in a thermal ensemble. So that's the idea, that you can get an effective temperature and you can get sort of the system to thermalize. The question that we were looking at for, yes.
Still feeling tempted to ask. I mean, if it's truly closed system,
Yes.
then how does the entropy increases? I mean, if you are going to the Gibbsian one, that is the maximal entropy state. It's a closed system. How can entropy increase?
Yes. This is a very good question, really. This is the old question, so to speak. Yes. So what is happening, of course, is that your information is not going anywhere, but it is sort of getting entangled, going into more and more many-body degrees of freedom. So it is spreading into non-local degrees of freedom. Scrambling, that is exactly what we'll get to. So the information is there, we just don't know how to recover it. So yeah, so that is exactly the point, that locally the information is basically lost to local probes. So when we're talking about this entropy increasing, that's essentially what we're saying, that if I am looking at this thing locally, it is locally indistinguishable from being in a thermal ensemble. Yes, but I was teaching statistical mechanics, and we go through sort of H theorems, and these are things that one discusses. Yes. Yeah, so that's the basic point, that this thing is lost, the information is lost to local probes. And how fast, the question that we were sort of interested in is that how fast does an isolated quantum system thermalize? And this is captured through this notion of exactly what you called scrambling. And in the fastest scrambling systems is such where the time that it takes to thermalize scales logarithmically with the number of degrees of freedom. Okay. So let me tell you a little bit about the notion of scrambling, because that came about, that this is the fastest thermalizing system are fast scramblers. So the notion of thermalizing is basically the following, that you have a dynamical process through which local information gets spread over many body degrees of freedom and gets essentially lost to local probes. So black holes basically are the fastest scramblers known in nature. And the question that we wanted to ask is that, are there classes of many body systems that can scramble as fast as a black hole? Now, this has been of interest in the recent past, and there have been some models which have been proposed. Let me very, very quickly just tell you my model and tell you that it does scramble as fast as a black hole. Okay. And so I'm going to go skip. But let me tell you what are the things that we need to scramble fast. So the first thing that you need is long range interactions, because what happens is, if you have a short range interacting system, then the system scrambles through a sort of linear light cone. So then the scrambling time will scale linear, split proportional to d, it will scale with n, but we want the t star to scale with log n. So which means that you need long range interactions. Okay. Which of course starts bringing us back to our old, the first part of the talk where we were talking about all-to-all interacting systems. So the first thing that we need is this long-range interactions, ideally all-to-all interactions. But all-to-all interactions alone is not good enough, because if you have a purely all-to-all interacting system, then you would actually end up getting sort of a integrable model, and so the system will not really thermalize. So the next thing that you need is non-integrability. So what we did was that this non-integrability is important for chaotic dynamics. And so what we did was we showed that if you have a model which has uniform all-to-all interactions together with an Ising interaction, such that one of them would give you non-integrability and the other would give you, the two of them together would give you non-integrability, and this would give you uniform all-to-all interactions, then I'm going to skip over all this. how does one quantify scrambling, but the end result is that we can show that this you have a system where the scrambling time can scale logarithmically with the system size, and this just requires these two things. It requires all-to-all interactions, and it requires something that will give it chaos. Interestingly, we discovered it, and at the same time, unknown to us, two other groups were pursuing the same question, and so they also discovered it. It came out on the archive sort of within 2 weeks of each other, so that was fun. But yeah, so then, but that's all that I wanted to say about scrambling, given our time, that we do have a got this insight that how does one scramble fast, what are the requirements. Okay, so with this, okay, so we skip everything and just finish off by again thanking you guys, thanking you all for attending it, and always a pleasure to be back at ISER. So thank you.
So the floor is open for questions. Yeah.
Sir, I have a question.
Yeah. First, just wait. Yeah, I'll first answer. Yeah. Go ahead.
Okay, so Sayan, so in the peak-top model,
Yeah.
so you are just focusing on the 2 cycle, but suppose there is also the
Yes.
possibility to have the n cycle.
Yes. I did not go into that. You do get that. You not only get n cycles there, you can even get fractional kind of cycles there. And one of the things that we have been also doing is in terms of if we go to this aperiodically kicked-offs, it turns out that the 2 cycle is very stable, but as you go to these other cycles, they're not as stable. So yeah, but that's absolutely right.
Also,
Yes.
it will be embedded with the chaotic regime.
Yes, absolutely. Okay, somebody else had a question?
I had questions.
Yes.
So in the first part, when you were talking about time crystal,
Yes.
so basically you were applying a periodic drive. So my
Yes.
question is, there is a phenomena called dynamical Casimir effect when you apply periodic drive very rapidly, and that causes particle production.
Yes.
Does that have any connection with time crystal?
Actually, okay, so somebody, I don't know about the dynamical Casimir effect, but apparently it does have relationships to time crystals. But you know, but this was again told to me by somebody, and I didn't really follow it up. But it possibly does. But I actually don't know the answer.
Dynamical Casimir effect is an analogous phenomena to Hawking radiation.
Yes. So what I was, so this is again, as I told you, that someone actually mentioned this to me once, that apparently the dynamical Casimir effect can be thought of as a time crystal. I have not really looked into the literature, so I don't know if it meets all the criteria to be time crystals. So time crystals actually have a certain set of criteria. I did not go through this. It's not just periodic, you want to have a system, firstly, ideally you want to have a system where you have this periodic oscillations, but then you would want to have it not for very special states, but you should, ideally you want to have it for a sufficiently general class of states. So whether those things are satisfied or not for the dynamical Casimir effect, I don't know. So, there are, and also for a true time crystal, you would want that in the thermodynamic limit, this kind of oscillations last infinitely long. So again, so these are things that since I don't know, I can't give you the exact answer, but yeah, there are possible connections for sure. Yes.
Okay. Thank you.
Hi, sir. What kind of quantum transport mechanism will it follow? Like when you are designing some quantum material, then there has to be some sort of transportation, right? So like what kind of quantum transportation we can talk about here?
Sorry, quantum transportation? Sorry, I did not get your point. Can you repeat the question again? Sorry.
Let me just write it down in the chat.
Oh, okay. Wait. It's somewhere here in the chat. Okay, is typing? Okay.
Shyam, has somebody really demonstrated experimentally this thing? Not, I mean,
Yes, time crystals.
NMR group.
Well, in India, yes, the NMR group and ISA Pune has also done it. There is a certain thing though that there is a few body time crystal because they have a particular star geometry which is essentially few body. But yes, this has been done with ion traps, for instance. Yeah, yes. Ion traps have been done. Chris Monroe. Yeah. So his was he was it was essentially few body, but it is a time crystal, yes, and it was the first example where it was done without disorder. Nothing has come yet, right? Okay.
Can I ask a question?
Yes.
Can you
Go
hear
ahead.
me?
Yes.
Thank you for your talk. What is the benefit of having time crystals? So what new physics one can see by considering time crystals?
So one of the things that was there in mind was that because these are such perfect oscillators, these will probably have uses in metrology. So for instance, even for the kind of time crystal I discussed, when we didn't go into this, you can actually get a, for if you wanted to sort of estimate a delta J, a period that actually can beat the standard Heisenberg limit, and you can get a 1 over n to the 3 halves scaling. So you can use this for metrology. That is one of the, if you think about applications, that was one of the applications that has been driving some of this research.
Mm-hmm. So could you suggest literature or maybe
it does. Yeah.
Self-educational purposes, yeah, right? To understand for self-educational purposes to understand the benefits of using time crystals.
So, I mean, the benefit, as I told you, is that essentially, if you wanted to, again, I mean, the idea was to do some sort of metrology, hopefully with these kind of time crystals, that you would be able to, with this kind of atomic setups in general, one of the ideas is that you want to build better and better clocks, right? And or want to do metrology, want to sort of, yeah. That's exactly the thing. So what? Yes.
What he's saying, I do not hear properly.
So basically, what? Okay, and go ahead. You can mention the. Yeah.
No, so what I was saying was that one of the candidates for a very, very long, I mean, precise clock was one of these transitions in the ytterbium ion, these octopole transitions, which would lose like a second in 3,700 years or something like that. So that, of course, experimentally realizing that is very tough because the transition probability is extremely, extremely low. It's an octopole transition, it's highly forbidden. But if you can actually get into this, I don't think that has been actually, probably they've shown some cross section, but getting a clock out of it hasn't been done yet.
Right.
But I guess if you really can get this time crystal thing more, reproducible or way manageable to a more commercial extent, then you basically have clocks which do not lose time at all. I mean, these are infinitely precise clock to whatever limit possible.
Yeah. So that connects back to your old comment about the fact that it doesn't increase entropy. So this stuff, and yeah.
I was just curious about something else, Shyam.
Yes.
So one thing that you were saying is that there's some recovery of the wave function and all that,
yes.
right? So in optics, when we have these very high angular momentum states of light,
yes.
So they have also, I mean, these these kind of topological charge, OAM, orbital angular momentum light. So they have this same property. So you will have them propagate to a distance and then they will self-heal.
Right.
Okay. So you can also show that depending on how large the topological charge is, you actually take a longer time to heal.
Right.
So you actually get the same angular momentum state back, even if you put an aperture.
Right.
You destroy the intensity profile, but the beam propagates and it becomes the same.
Right.
Again. So is there some kind of possibility of extending that thought to, I don't know, I mean, because here also you're sort of recovering the wave function after some kind of time, right? So,
Right. Yeah, and I mean, it's very possible. I mean, one of the whole thing at some level boils down to robustness, that as I add different kinds of perturbations. So one of the goals with these time crystals is that these should be very robust. I keep adding perturbations and it will still, I may not recover the exact state, but in terms of the oscillations will continue forever. So that
zero damping, that
zero
is.
damping essentially. So that is something that one has to figure out, that maybe it is maybe things are robust to certain set of perturbations. Are they robust to enough set of perturbations, let's say? So that's one of the things to figure out.
Yeah, so one analogy comes into my mind.
Yes.
Regarding quantum metrology, which can be done by also using correlated photons coming from PDC process. So I think time crystals also have some quantum correlation of particles.
Yes, it does.
Yeah. Okay.
Yes, it does. It does. And again, in terms of the idea is the goal was always to try to build this better and better clocks. And I think right now the best clock we have is this Ytterbium SUN kind of clock. That's what Yun Ye has at Chilla. The goal here is that probably, you want to beat this in some way and to get very, very good, essentially a perfect clock, so to speak. So yeah, so that
Thank you.
that's still not there yet. Hopefully something good will come out of this.
Thank you. At least I got the idea. Thank you.
Okay, so what happened to Mr. the other one? Is it still typing? No. Okay. What was his name?
His name is
Gagat. Mr. Gagat, have you finished typing or?
he seems to have left.
Okay. Okay. So if there are no further questions, let's thank Sayan and everybody who attended. Thank you.
Thank you.
Thank you.
Thank you. Bye.